block management, LBN headers and markers table. That's basically a last step of the data recovery process, data recovery case. And first of all, let's see full process of data recovery. And on this diagram, you can see step-by-step transformations that we need to do through physical dump in order to convert that dump into logical dump. So first of all, we let me run this thing here, spotlight. So first of all, we have physical image, and then on the next step, after we got physical image, we need to do page layout. That means that we need to set borders of data area, service area, ECC, and so on. So we need to let our software know where is what, where is all structures inside the physical dump. After this, we should apply ECC. ECC is a very important thing for modern devices, because without ECC, all data will be just totally corrupted. By the way, last our update can do that page layout thing and ECC together in one step. If ECC is supported for the device you have, then you can run ECC search, and if ECC will be found, software will offer you to set data areas and ECC areas. So all you need to do after this, it's just to set header and LBN. That's it. So we did page layout and ECC, right? After this, software knows where is what. And yeah, by the way, what about my speaking? Does everybody understand what I'm saying, or maybe I should speak slower? Do some response in the chat. All right, great. So after the ECC step, we need to apply either inversion. Let me move my microphone a little bit. We need to apply either inversion or XORed transformation. For older devices, we apply inversion because data could be inverted. It's like 0 to 1, 1 to 0. And for modern devices, basically for all devices that we get nowadays, we need to apply XORed transformation. So we need to convert noise from in physical image into some data patterns. After we apply XORed transformation, we need to deal with page allocation analysis. What is that? A controller can write data can write pages in several ways. It can write data into several chips simultaneously, or it can write data into one chip, then to another chip. It can write data simultaneously into same crystal, into several crystals of the same chip. So all the things we need to figure out on this step. And once we understand how pages were written into the chip, we apply some transformations, or maybe we just skip this step if all the pages were written just sequentially. Yeah, and on this step, we basically have good data integrity within one block, because let's say we don't have ECC errors, we don't have XORed transformations. All pages go sequentially within one block. And the last step we need to do, it's a block management, because blocks are mixed in the dump. They are mixed due to where leveling algorithm. If you remember, if you know this, controller doesn't write data sequentially into physical dump. It writes one block to one place, next block may be written in another place, and so on. So all blocks are written randomly to make all of them used approximately on the same level. So after page allocation analysis, we have data integrity within one block, but blocks are mixed. And this webinar will be about how to figure out how the blocks are mixed and how to arrange them in logical sequence. Oops. So this is what we have. This is what we have on this step. We finished this part, and we have on this step physical dump. And that physical dump consists of several types of data, several types of blocks. Some blocks are related to firmware, so they have firmware. Some blocks have actual user data. When I say actual user data, I mean the data which user had on the device in the last moment when device was good, right? Just before a device got broken. So that's the actual data. However, the physical dump may have also some out data or obsolete data. The data which user time ago deleted, but the data are not available anymore by logical access, but they may still present in the physical dump. Just recently we got one nice case. I think we will do some video about this. When memory card was formatted in some camera, Sony camera, Sony camera, and logical dump looks like totally zeroed. There were just zeros inside, and of course no logical. I mean, the card was good. It provided access to all the sectors, and everything was good. But there were just zeros by logical access. So we soldered this card to our adapter and got access to physical dump, and physical dump was full of data. Okay, David. Let me answer. So we analyzed the data, and we could find pictures, videos, and it was a wedding case. And that photographer was really happy because he tried many softwares which didn't get him any access to data. And we could, well, not many, not much of data, but still we could get it. So it looks like controller just, didn't show real content of the physical NAND, but just kept showing the zeros, which are artificial zeros, in fact. So controller may have that obsolete data, and there could be also cache data. Normally, when we deal with regular data recovery case, we don't want that cache data or obsolete data. We want just that actual data, the data which were lately available on that device. So on this step, our task is to filter out that all the blocks which don't have actual data blocks, which we can see here on this screen. So we should remove all firmware blocks, obsolete data blocks, cache blocks, empty blocks, not used blocks. So everything. Just data blocks should still be in the physical dump. And that's the first step. And we do this step by the header. What's the header? I'll tell a little bit later. Guys, could somebody help to David, which we can see messages in the chat, to figure out what's wrong with the voice, because I think it's just a matter of some clicks in the Zoom application. Type him to maybe to use computer sound or PC sound, something like this, and then it will work. And I will proceed. So that's the first step, what we do on the block management stage. We delete all the blocks which we don't want to have in a logical dump. After this, we have only data block. And the next step would be to arrange all the blocks in ascending order. If you remember, I told you that blocks are mixed. So block number 0, very first block from logical dump, could be located anywhere in the dump, in physical dump. In logical dump, it's located on the first position. In physical dump, it will be anywhere. And our task here is to arrange all the blocks by their LBNs. LBN stands for logical block number. So we need to arrange all the blocks in ascending order by LBN. Block number 0 will have boot sector, MBR, next block may have FAT tables, and so on. So if you want to get logical structure, file structure, this step must be done. And now the question is how to do this, right? So what we're gonna do? To proceed to understand what we're gonna do, first of all, let's talk about header and LBN. So what is header and what is LBN? It's usually it's 3 bytes in service area. 1 byte belongs to the header, and 2 bytes belong to the service area, to the logical block number. And the header, that 1 byte, it shows type of block. I mean, each block has that header. And the header describes type of this block, where this header is located in. So the header may mean that this is data block, this is firmware block, and so on. So the header describes type of the block. And logical block number defines position of the block in logical image. This screen is kind of complicated. It has many text, but I suggest you to have a look on this screen when you will do your cases, because it has all necessary, all important information for the header. Let's say it has some facts about the header which you should remember. So as I said, the header is 1 byte in service area. It defines type of the block, where it's located. And this header, or let's say header of data blocks, it may have different types. It depends on controllers. Usually for Phison controllers, we have one specific value for the header. It could be, usually it's FF or 0 or something else, but usually it's FF or 0. So one specific value for the header. Oh, by the way, let me check if the recording is going on. It seems it's on. Yeah, and it's typical for Phison controllers. Sometimes Phison controllers may have several specific values, such as FF and 50. For example, 50% of data blocks have header FF. Another 50% of data blocks have header 50. So two headers, two values for data blocks. All another values means that it's not a data block, it's something else. We don't know what else exactly, but not data block, definitely. And SM controllers, silicon motion controllers, they use a range of values for data blocks. Typical range, it's 20 from 20 to 3F, range of values. That means that all the blocks with a header 20, 21, 22, 23, 4, 5, and so on, until 3F, all the blocks belong to data blocks. And we should put all the blocks into the logical image. And if we will find some block with a header like 18 or 43 or 40 something, then we don't use that block. We just skip them. And the question is how to understand what the header we have in some specific case. We assume that most of blocks with data, they belong to actual user data blocks. We don't talk about empty blocks, which have just FFs. We talk about blocks with data, with like data looking patterns. So we should analyze what headers that blocks have mostly. And if we see that most of that blocks with data have header FF or 00, this tells us that data blocks in this specific case have header FF, for example. Or if we deal with the same controllers, we see that most of data blocks have headers like 21, 22, blah, blah, blah. So we understand that that's a SM controller, that header has range of values, and we need to take data blocks into the logical image. And in this area, you can see that rule, which can help you to work with headers. So to filter out blocks without actual user data, it's necessary to keep just user data in logical image, it's necessary to find the header that the majority of the blocks with data have, and then just remove another blocks in other headers. Then we just should say to software to not use blocks with the headers and other than that majority of data blocks. So it's just a statistical thing. We have a look on blocks with the data. We just visually detect what majority of blocks have, and we understand very easy that data blocks in this specific case have header like this or like that, like FF, for example, or FF50. And yeah, then we set this information into the software, and then software will automatically remove all the another blocks with another header. Okay, so one more participant. Right, so that's the header information. Now let's see what we have, what we can say about LBN. LBN stands for logical block number. It's 2 bytes in the service area and defines number or position of the block in the logical image. That means that very first block with boot sector or with MBR has LBN 0000. So something close to 0. And in why can software automate? Well, it will do this. Actually, we are about to redo markers table, but it's a really huge work, and it will take a lot of time, and we want to redo this really big, and it will have some automatic things, and probably it will you will have to do much less work with markers table. But as I said, it will take time, and until that, we need to do this manually. And there are some things which may help us to do this manually, but still, most analysis you do by yourself. Okay, so in this area here, we can see typical LBN ranges. It's quite an important thing, because sometimes LBN may start just from 0. Like very first block will have LBN 0000. And it will be the first block, and the last block number could be 3FF, 7FF, FFF. So these values will be standard. But the very first block may have number 0000, or it could be 1000 or 1000. And then that one will just be repeated. Or actually, like first digit in this byte can be anything. Well, like not a digit even. It could be F, for example, or 4 or 8. It depends on controller. So we don't care about very first symbol in the byte number of the first byte. We want to see zeros on those 3 positions. If we can find such block, and if we see in that block some structures that look like NBR or boot sector, so that's the first block, first logical block. If we don't see this, then we need to try to search more. Maybe just empty block. Well, I'll show this on the real cases. Well, the webinar is recording, and we do want to make this webinar available, but it's our first webinar, and if everything will be fine, if everything will go smoothly and video will be good, then we will make this available. But yeah, I think, let me say like this, we will do everything depending on us to make this webinar available, but if something will go wrong, so unfortunately, yeah. Since this is our first experience, we can't be sure for 100%, and we can't promise this. But I hope that it will be available for sure. So the first symbol of the LBN could be any. That's about typical ranges of LBN. And another two things that you should take into account, that LBN could be inverted or could be recorded in Little-endian order, Little-endian format. So what does it mean that in LBN is inverted? Sometimes for some old cases, you may use inversion on some previous step, like I showed here. So let's say that you have some old case and you used inversion, and this tool, this element will invert everything in the dump, in physical image. It will invert data area, service area, and so on. But usually only service area is inverted. And no, only data area is inverted and service area is not inverted. And in this case, you will artificially invert service area, which is not necessary. And then you will see inverted LBN in the markers table when you will analyze that LBNs. And you will have to invert LBNs back. And another thing that it's typical for silicon motion controllers, there is no inversion step. For that cases, you use XORed transformation there, but service area is inverted there. So you need to invert it. So you need to apply inversion in markers table to see normal values for LBNs. No, whole dump couldn't be in Little-endian. Just LBN could be in Little-endian. So LBN may be inverted, and how can you understand that it's inverted? You just scroll LBNs from whole dump, and you don't see anything close to 0, 0, 0, 0. All numbers are too large. You can find any sequence, growing sequence, or any chain of LBN. So you should check that maybe LBN is inverted. And the second thing, LBN is written in Little-endian order. How can you see that? For example, you selected some 2 bytes for LBN and you start the analysis. And you see that first byte, high order byte, is actually growing, continuously growing. Like you can see group of here on the next screen, we can see it. So you can see group of like high order byte 0, 0 here, you see, then 1, 2, 3, 4, 5, 6, and so on. If we will scroll this chain, we'll see that high order byte, first byte, is continuously growing, and second byte just keeps several values like 0, 1, 2, 3, 0, 1, 2, 3. So in this case, probably that LBN has Little-endian order, and you need to just switch positions of these 2 bytes. You need to put this byte, second byte, on their first position, and second byte on the first byte on the second position. And after this transformation, it will look good. It will look normally. So that's 3 things about LBN that we should take into account, that we should remember. Now let's see where that LBN and header are located. Most common controllers, most typical controllers, it's which we will discuss in this webinar, it's SM controllers and Phison controllers. And usually SM controllers have service area in the end. So page structure would be like data area, ECC, data area, ECC. And at the very end of the page, you'll see service area. And service area structure will be like this. First byte belongs to the header. Then we have 2 bytes going on for the LBN. And then there is some gap some 2 empty bytes, and then we have our ECC for service area. These lines belong to ECC for service area. And that's typical structure of SM controllers. So once you deal with SM controllers, you can just from the start assume that first byte belongs to the header, next 2 bytes belong to LBN, and then you can check your suspicion, your guess in the markers table, if it's right or if it's not right, if it's not correct. So that's SM controllers. The Phison controllers have a little bit different structure. The difference is that between header and LBN, they have 1 empty byte. So the first byte is the header, the same like SM controllers. Then we have 1 empty byte, some gap, and then 2 bytes, which are LBN. So once you deal with Phison controllers, you can set first byte for the header, next 2 bytes for the LBN. Yeah, that's the location of header and LBN in the service area. And the thing is that different devices have, anyway, they have different structure, well, structure could be the same, but like sequence of LBNs may be a little bit different, or header may be a little bit different. And it's pretty hard to make some precise script how to work with the markers table, what to do. But I try to do this anyway, and we will try to follow this diagram, this algorithm, when we will work with markers table. Yeah, let's discuss it now, and then we will come back again to this diagram later. So once you got some list of markers, some list of LBN, you need to click to the block sorter button, and it will sort all the LBNs in ascending order. It will try to do this. And then you should just scroll whole LBN list and check visually if you have ascending order of LBNs, like this one, 000, 001, and so on. And if you have this, then you proceed with these steps. You need to try to filter by header, which we discussed before. We need to add banks, which we will discuss later. You need to work with filter for LBN and so on. If you don't see this sequence, then it means that there could be 3 possible reasons. LBN may be inverted, LBN may have little-endian order, or you just selected wrong pair of bytes. Maybe it's not LBN at all. And you need to try another pair. Sometimes it could be not that obvious which 2 bytes you need to take for the LBN, and you need to play with this. So that's the plain script which may help you to work with the LBN. Oh, by the way, I forgot that I will share this PDF file with you. So you can use it right now, and you can use it later. So let me send you this file. Send this one. Open. All right, so now I think that we can start cases. Everybody got a PDF file, markers table? All right, great. So let's see the VNR and cases I prepared. I mostly used cases from our basic training, but also we have so some of you who was on my who was on our basic training may be familiar with the cases, but there are also new ones. So the first case would be, yeah, this one is very typical, very standard. And it looks like this. And now I would like to, there are some people on this webinar who don't have our tool, VNR. And I'd like to show briefly the data recovery process. And maybe for some of you will be interesting to how it works now. Do you? Yeah. So I will proceed with markers table. Yeah, maybe later. So we have physical image, and if you remember our first step here, it was page layout and ECC, then XORed transformation, page allocation analysis. So let's see how do we do this in visual NAND reconstructor. We have physical image, and if we do double click, we can see content of the dump. Default view of the content is bitmap view. It's a little bit different from another tools, and this is our good part, that we have very powerful bitmap. So each pixel here means 1 bit of information. Data goes horizontally, so it starts from the left and goes to the right. And 8 pixels means 1 byte. If you zoom in, you can see these borders. So this yellow area stands for 1 byte, orange area stands for next byte, and so on. Data is written horizontally, and from the left side to the right side, you have one page. So when you scroll it horizontally, you scroll pages. When you scroll it vertically, you scroll blocks. And the very first thing, as I said, it's necessary to do page layout. I have page layout here already, and let me remove it. So now software knows just information about blocks and pages. Software knows block size, software knows page size, and where are blocks, where are pages, but software doesn't know anything about page structure, internal page structure, where is data area, and so on. And we can try to use ECC correction, ECC element, in order to adjust page structure. So I will run this option, find code words. I select Phison controllers, find. Here. And that's how ECC search works. If we have this in database, pretty quick we can find necessary code word, necessary settings for BCH element. And I do remember that this is controller PS2251-50-F, so I select this one, which is 99% will be compatible to this case. And now software should ask about structure, but seems we have here structures. It doesn't ask me. So if you deal with a new case, software will ask you, once it will find necessary code word, software will ask you if you want to add data area and ECC areas to the structure. I need to create new case and start from the beginning to show you this, but if you have really a new case, it will do this. You can't find code word probably because you don't have it in database. Check if you have, you should have, well, that's for configurations. You should have ECC code words in VNR database, which is located in program files, VNR folder, then database, and so on. Okay, so we have physical image, we have ECC, and let's do that page structure. I will not go into details now how to search that page structure. Maybe we will do another webinar for this. By the way, maybe somebody didn't see, but we ran kind of a poll on our community center in support.rusolut.com, and you people could select first topic for the first webinar. If we will consider that this format is good and you want to proceed with this format, with these webinars, we can select next topic, and you can share your opinion what should be the next one. Okay, maybe it will be about page structure, maybe about something else. So how do we do page structure layout? I need to do double click, then I mean, this area now is undefined. So how to define this? We do double click and select from drop down menu data area, which is 1024 bytes, and I set position. Yeah, the version is 3.8, as far as I remember. We need we set position. Start address would be 0 because page starts from data area, and stop address will be 1023. With that coloring, I can control if everything is correct. So I see that it starts from the start data area with this color, and it ends just before service area. Then I have 1, 2, 3, 4, 5, 6, 7, 8 bytes for service area. Like this. And then I have 42 bytes for the ECC. And how to detect ECC size if I don't see the border between ECC and data area? I can just scroll to the end, and here, after last service area, I can measure. I can make left click to the first byte of service area, right click to the last byte. Oops. And I can see here that it's 42 bytes. So I add ECC here, and then after ECC, next data area goes. So I can copy that, paste, and I have service area again. And the thing is that this controller has second and third and so on service areas smaller than the first one. So I select this service area, which has size 4 bytes. And then ECC goes the same one, 42 bytes. And so on. And after this point, I can just select 3 of these structures and click Ctrl V, like this. And it will fill the page fully. So from the start and until the end. So that's page layout description. That's what we do on page layout step. Now, software knows where is what, where is data area, where is ECC, and so on. After this step, I need to apply XORed transformation. And to do this, I will use our XORed analyzer tool. I will run it on ECC element. Again, I will not go into details how this tool works. Maybe it will be another topic. Now I'll just show briefly how it works. So once I run it, I can start auto detection. And it found something. After detection, it found some blocks where I can try to apply XOR keys. So from the left side, I have now list of blocks where most probably I can check XOR keys, which I have here. You see the mouse here, which I have here, and then I can check compatibility. So for example, let me try this. I click to validate key, auto. Yeah, and it's saying that this key is ideal. I have 99% that this key is good for this case. I can check it with another blocks. Yeah, these ones, and it will just confirm now that there are keys that 50% good, and this key is 100% good for this case. So I select this key and click to apply XOR, and I have XOR now here. So data is not XORed anymore. All your suggestions about webinar you can write in the community. And people can vote for this. So now we have data, okay? The next step after this would be, let's see what, it's a page allocation analysis. So now we need to check how the pages were written into this chip, sequentially or simultaneously. The chip may have 2 planes. One plane, it's an array of memory cells in one chip. And to detect this, I need just to check if I have repeatable patterns within one block. To do so, I run option to highlight blocks. And let's see if we have repeatable patterns. When I say repeatable patterns, I mean something similar from the first part of the block and from the second part. Like, for example, this line, we can see, well, this is one block, right? This black colored block, it's one block, one logical block. And if we divide this by 2, we can see one line is here and the same line is here. I'll not explain now why that means that we need to use the pair element. Just trust me, maybe we will do this on another webinar. But for this case, we can see that repeatable patterns many times. So we have it here, here, then again 2 lines, 1 line here, 1 line here. So that all says to me that I need to use, I need to deal with multiplane page allocation, and to deal with that multiplane page allocation, we have a pair element, which I just connect like this, and that's it. So after this step, we are on this level, on block management. So we have data integrity within one block. Data is not XORed, data pages are not mixed within one block. And all we need to do now is to make the things I told you before. We need to remove not data blocks, and then we need to arrange data blocks in ascending order. But first of all, to do this, we need to analyze service area, and we need to find that LBN and header. So I can come back to physical image, to bitmap view, structure view, and if you remember, LBN and header are located into service area in here. So I jump into service area, and now I can set here where is LBN and where is header. There are several approaches how to do this. First, I can just scroll the dump vertically, and I should check which 2 bytes are changed from time to time. And that 2 bytes would be LBN. Because if you remember, I said that blocks go vertically in the dump. So from this point to this point, we have 1 block. Let's highlight them. So this is 1 block. Then we have next block, and so on. Each block has own LBN number. So whole block, all pages in this block will have the same number, same LBN. And that LBN is written in service area. And we can see this as like same pattern of lines within 1 block. You can see these 2 bytes, right? No, those 2. And we can see that from time to time, value of these 2 bytes are changed. Maybe to better understand, let's run hex. And here you can see highlighted these 8 bytes service area. Yeah, and we pay attention on 1, 2, 3, on 3rd and 4th byte in service area. So we can see that in here, if I click on any page within this block, LBN is 1242, right? And from this point, we can see that it's changed a little bit. And it's already at 1243. So it's everywhere at 1243. Then we have 1244 here. So let me summarize. To find the LBN, we can just scroll. If you don't know even in advance, if you don't have some ideas where is LBN, you can just scroll and check 2 bytes which are changed mostly and regularly from on the same distance, because block size is the same within whole block, within whole dump. So if you see that from on the same distance from time to time, some 2 bytes changes its value, it's very probably LBN, especially if we are talking not about silicon motion. So those 2 bytes are LBN. And another thing that let's set this. To do this, I just make double click, select LBN structure, 2 bytes, and set position starting from byte number 2 and until byte number 3. Okay, and now it's highlighted. So now I can scroll it, and we can clearly see that bytes, these 2 bytes. And if you remember, Phison controllers typically have location of header and LBN like this. So first byte is the header, then 1 empty byte, and then 2 bytes belong to LBN. So that's what I'm gonna do now. I will set first byte as a header like this. And just in case, if I'm mistaken, I can set 1 test byte and select this byte as a test byte. So now I did this selection based on these changes from time to time, and based on experience that usually I know that Phison controllers have structure like this. Once I did that guessing, I should check it. And to check it, I go to header don't have lines as LBN. Well, it depends. If header has just 1 value, like Phison controller, and most of blocks have header FF, then yeah, header will not be changed. But if you remember, I told you sometimes header may have a range of values, like SM controllers. And in this case, header will be also changed from block to block. But it's typical for SM controllers. For Phison controllers, LBN will be, most of blocks will have the same LBN. Okay. Now, how to analyze that headers and LBNs? I drag and drop logical image element, which will create logical image, and marker stable tool, which will help me to analyze and to arrange all that things which we just was selected. So in marker stable, we have parameters in this area. In this area, if somebody has video from the right side, you better move it now, because parameters of markers table are located from the right side of the screen. And then these parameters, we can set positions for LBN, for header, for test position, if we want to test it. That's number of bytes. And when we run this option, when we run this operation create table, software will scan those bytes from each block. 10, 26, 20, 27 bytes from each block from the first page, and will create list of that values and place it into the table, which we will analyze later. And the software took these numbers just from here. When we did set header, LBN, and so on, we set position, where are they located? And software took it from that positions. So that's why we have now they are set here. So now let's click to create table, and software did read all the values from these bytes. And next step would be analysis of that values. To do this, I do double click, and that's the list of LBNs, headers, and test byte. This is how it looks like. And what do I have to do here now? I need to do these two things. First, I need to remove all empty blocks, obsolete data blocks, firmware blocks, and so on. And then I need to arrange all the blocks in ascending order, like on this picture. And how will I do this? Let's try to follow to this diagram. So first of all, I will click to block sorter, and I will scroll whole LBN list and check if I have ascending sequence. The block sorter button is here. So I click it, I leave for default settings. And now all LBNs are sorted. And now let's just scroll it. I see zeros now, and those zeros, it's just some empty blocks. And have a look from this point. I start to see growing sequence like 1000, 1001, 1002, and so on, 44, 45, 46. So the sequence is growing. And you remember about typical ranges of LBN. LBN may start from 0000 until some standard value, or from 1000 until something, and so on. So if I see this 1000, I suppose that my LBN position is good, and I don't need. So the answer on this diagram would be yes, right? Because I see ascending LBN chain. I have it. So the next step would be filter by header. Filter by header, and let's see how to do this. I told you that to select header, we need just to analyze statistically what header most of blocks with data have. These blocks we don't take into account because it's just zeros. If I open this block, I can place it to the side and run option synchronize with dump. So now I can see content of each block if I click on this block. So you see that these blocks, it's empty blocks. And these blocks with the numbers, they have some data. So I need to analyze, I need to check what header most of these blocks with data have. And to do this, I just scroll it. And I can see very clear that most of these blocks have header FF. And just some of them have header 47, 58, and so on. So very quick, I can figure out what header I have here. And by the way, let's see like this example. You can see that I have here 3 blocks with the same number, 10E9, 1, 2, 3. But only one of those blocks have header FF. So, and the first block with this header, it's almost empty. It has just some small amount of data. This one even less data. And this block is full of data. So this is how header helps us to filter out blocks with unnecessary data, with some cache data or obsolete data. We have 3 LBNs, but just one has good data, the data which we want to place into a logical image. So once I found that the header is FF, I can run block filter. And to do this, I click to this button, block filter, and I can set what blocks I want to keep in use. Now I filter it by header, so I select header, and I have specific value, one value for the header. So I leave this rule set. There are several rules I need set. So header set to FF. And that's it. In case if I have more headers, like 50% have headers 50, another 50% have headers FF. Then I can set one more rule here. But I don't have it, so I have just one value, so I use just one line, one string here. I click to OK, and let's see. You can see that only blocks with header FF now checked. And this checkbox means that software will take this block into the logical image. If LBN is unchecked, then this block will not go to the logical image. And this is what we want. We want to move to the logical image only blocks with header FF. Okay, let's come back to our diagram. Here we did filter by headers, banks. Let's skip it for now. We'll talk about this in the next case. And then we need to make filter by LBN range. LBN ranges may look like this. So we know that it starts from 1000, and the last could be 13FF, 17FF, and so on. So let's check what do we have in our case. Yeah, and don't forget that after each step, we click on block sorter just to check what we did, if it's all good, if we did a good preparation, good modification, or if something is wrong. Okay, let's go back to VNR. Click to block sorter. And now I can see that it starts from 1000. I can run here hex view. And I can see MBR here. So it's all good. It's correct. Next block is empty. Next one has FAT tables. So it's all right. It's all good. Now I need to filter it by LBN range. And it starts from 1000. Now I will just scroll it. And again, just visually check where sequence will finish, will end. You see that it's like 1000, 1, 2, 3, 4, 5. So approximately, I can see that it's growing approximately all the time. It's growing, it's growing, still growing. Oh, and now I have that FF blocks. And the sequence is going until 12F3. Because you see it, we have like A, E, A, B, C, D, E, F, then F0, 1, 2, 3. And there is then a huge gap between 12F3 and 1777. I think it's just some mistake or some garbage block. So in my case, in this case, the last block would be 12F3. So I can run that block filter and set range of LBNs. Range would be from 1000 and 1. Well, basically I have here two options. I can set precise last LBN like this, like I have here, or I can just don't care and set some standard value, because I see that this LBN list is located within this standard value. It's not going out of this range. It will have the same effect. As you see, I clicked and all these empty blocks just unchecked now. All right, so we can click one more time on block sorter, and yeah, everything seems to be fine. Let's see what do we have after this. So we did filter by LBN range, and the last step here would be check LBN, to check LBN chain. We need to do two things here. We need to remove duplications, and we need to insert missing blocks. What is that? What does it mean? Remove duplications. Do you remember I showed you that we had 3 blocks with the same LBN, but only one of those blocks had header, which allowed us to select the good block, and we just leave that block in the markers table, and other blocks we unchecked. But sometimes there could be a situation when 2 blocks have same LBN and same header, and software will not remove automatically that unnecessary block. We may have 2 duplicated blocks because of bit errors, because of some mistake or whatever. There could be many reasons of this. And we need to remove that duplicated blocks. We must remove them, because if we keep these blocks in logical image, we may have this problem. So in here, we can see good logical image. So we can see that it starts from boot sector, then FAT table. Then FAT table has links to, let's say, some pictures. One picture is located in this block, one picture is located in this block, and so on. And in this case, everything will work fine. That links will be correct, and we can read these pictures. We can get access to these pictures via file system. We can run a file explorer, and we will see folders, everything, and the pictures in that folders. Okay, I lost the mice. Are you guys still here? Okay, and the mice is not here. Okay, gotcha. Okay, let me try another mice. I have one spare. Okay, it's back. So FAT table has that links, and in good logical image, those links will be correct. And we will get access to the pictures via file system. In case if we create logical image with duplicated blocks, we do not delete the duplicated blocks, we will have this problem. Until some point, data access via file system will be okay until this point. But after these duplicated blocks, you can see that we have here two blocks with number 3, this one and this one. So whole this area will be shifted, but links stays the same. They still have the same numbers, same offsets from here. And as that offsets are the same, but in fact, like real offset now is different, whole file system will be, I mean, files which are located in this area will not be available in File Explorer. So that's why there must not be any duplicated blocks. We should remove them. So that's the first thing, duplicated blocks, which we should fight against. Another thing that here, and this screen shows what will happen when we remove duplicated blocks. We remove these duplicated blocks, and all this area will be just shifted like this, and there you go. You still have access to, you have access again to all these pictures, and file system is good now. So that's duplicated blocks. The same thing, almost the same thing, happens when you have some missing blocks. Reason of missing blocks could be the same. There could be some bit errors which changed block number and you just don't have some particular block number. Or there could be some reading problems, something else. So sometimes it happens that we don't have all blocks in the chain. And again, in good logical image, we have all links available, everything is correct here. But what happened if we lose one block? For example, this block number 3. Until this shift point, everything will be good. But after this point, after this border, this area will be like, this area will be shifted to the left. And again, since offsets from FAT table the same, stay the same, real offset will be different. those files will not be available via file system. And for this case, we need to insert some empty block, just artificial empty block. And this empty block will shift this unavailable area to the right. And again, after this, we get access to all the data. Sometimes you may see this problem like this, like you assemble image, you go to file system and you see that part of file system is good and another part is bad. And that could be because of this. By the way, our next update will have option to check, to search the place where you have this shift start. It will check each file and will tell you number of block where you start to have the shift from. Okay, so that was about this. Check LBN chain, remove duplications and insert missing blocks. Let's do this now. To do this, I go to the first block and just click on this button, check LBN chain. Oh, and here it's all perfect. I don't have any missed blocks. I don't have any duplications, so that's ideal case. I don't need to do all the things I showed you before. In other cases, we will have to do this. But here it's all good. Once you see this message, you can be proud of you that you did everything correct, and it seems that you will get good file system. So you click to OK, and then you just go to markers table and click to this button, create logical image. OK, there you go. You have now logical image on this element. You can run file system viewer. And yeah, you have these pictures. And the next case would be this one. Open case, no. Yes, silicon motion controller. So structure of the recovery of the solution, it's pretty the same. We have physical image, then we did page layout, then ECC correction, XORed transformation, pair, and now we are about to work with markers table. If we open markers table, it's empty now, and so we need to set here LBN position and header position. This is SM controller. So if you remember, SM controllers have location of header L and LBN like this. So they have a data area plus ECC before several times, and then in the end of the page, each page, they have header, LBN, and ECC for the service area. Let's see this. Okay, I opened physical image. Go to the data area. And now I can scroll it. Yeah, let me run structure view where I can see all structures. Structure is here already. We did this before. So you can see that this is data area, then ECC starts, next data area, yeah, next ECC, and so on. And the service area is here. And from the very first time, it looks kind of complex and you may not get where is what here, and it's okay. But after I tell you that first byte is the header, then we have 2 bytes for LBN, then 2 empty bytes, and then ECC, you should just remember this and use this information for all your next SM cases, Silicon Motion cases. And the good thing that SM is kind of popular controller. So, and the structure, most of cases the same for that SM controllers. So to set header, the header and LBN, we just dive into service area. Service area is undefined for now. Then I do double click, and now let me set the header, since the header goes first in that service area. So header, it's 1 byte, start address 0, and stop address the same 0. Yes, this is just 1 byte. And then 2 bytes belong to the LBN. LBN is here. And now you can clearly see that we have 1 byte, first byte for the header, then LBN, and then several empty bytes, well, actually 1 byte is empty. Okay, AirPods is off. So now we'll know real charge time for them. Yeah, 1 byte is empty, and then some number of bytes for ECC. So the header is the first byte, then 2 bytes for LBN, and then ECC. We want to work with those 3 bytes. Okay, we have it. Now let's go to markers table. And select LBN position in parameters. It's here. LBN, and the header position. It's here. And then I click to create table. Yeah, I would ask to, discuss things which are not related to the stuff I'm talking right now a little bit later, because if somebody will get some question about these things which I'm explaining now, I may just skip it because of the talks. Okay, so now I click to create table. I have the table. Is it for everybody? Voice is not good now. Okay, let me try to fix it. Microphone stays the same. Okay, let me just switch it quickly to another microphone. Okay. Microphone, this one. Okay, what about now? Is it better? Okay, great. So we continue. Great. So let's proceed then. markers table. Yeah, I clicked to create table, and now I have the table. Let me repeat that each line here represents one block, and each number here, it's this LBN, it's a number of LBN, and the header, it's a header value. So, do you remember what should we do now? Let's go to the presentation and check this diagram. So the first step, as usually, we click to block sorter, and then we check what we see there. All right. So I click to block sorter, and now I need to scroll whole. The chain, whole list, and check if I see growing sequence, growing chain. So it's just zeros here, and then some numbers starts, FD, and it's kind of growing, but the very first number is FB63, so it's not close to zero at all, right? And then it's growing, but there are gaps, and it's not good. It's not beautiful LBN chain. It's not what we want to see here. And we do want to see here something starts from zero, something like F00 or whatever. And it's not this, it's not the case. Okay, let's go back to the diagram. And we did scroll whole LBN list, and we don't see LBN chain growing. So the answer is no, right? And what do we have to do now? We need to try all these three steps. And first one would be check if LBN is inverted. And actually, it could be the reason of such situation, because if we go back to this example, we can see that if numbers are too large and not close to zero, so probably you have that inversion case. And since this is a SM controller, it's quite typical for SM controllers to have inverted LBN. So let's try to do this. To invert LBN, I will use this option, marker set it. Oh, by the way, markers, marker, it's the LBN. Markers table, it's LBN table, marker set it, it's LBN editing. So I click to marker set it, and I will invert, I can invert here LBN. To do this, I click this checkbox, and of course I need to invert header, because they go like together. If LBN is inverted, then header is inverted too. I click to OK, and then what will I do next? I will click to block sorter again. I start that this routine from the beginning. I click to block sorter, check again the list, and so on. Okay, so let's do this. Block sorter, okay, and let's scroll it now. Until now we have zeros. And have a look. We have zeros, then several blocks with number 1, 2, 3, 4. And basically it's starting to grow. You see? It's keep going. So now I like it much more. It's going up, going up. Yeah. So I see growing sequence. I see growing chain. And once I see this, I switch to these steps. And now I need to make filtering by header. Let's see how will I do this. Headers. As you can see, all of them have different values. So it's not the case like before when I had just a FF header and only several blocks with another header. Here we have very different headers, and we need to figure out which headers mean data blocks, actual data blocks, which headers mean something else. Let's remember this slide. So headers. In previous case, we had this case. So we had one specific value. Now we have range of values. And that's very typical for SM controllers. So we need to set this set of range, range of values. And the question is how to detect this range. Because, well, basically, in many cases, you can just set standard range, like from 20 to 3F. But it's better to detect exact borders of this range. And to do this, it's quite easy to do this. We can click to block sorter, but now I uncheck this default option, and now I have list of let's say priorities which software uses when it sort the blocks. So default priority is like this. It first pays attention either this block is in use, then it pays attention on bank, LBN, and only then on the header. But if we set, let's say, header instead of LBN, so software will ignore LBN and will sort all blocks by headers. And why do I want to do this? Because now, if I scroll blocks, I will see where headers range starts. You see, on this point, I had 0, and then it starts from 21. So 21, it's the number where a header starts. And then it's growing, 21, 22, 3, 4, 5, and so on. And I expect to see it growing, it's growing until 3F, more or less. And now I'm checking, like, now I'm trying to find the place where this chain will break, will stop. So until 31, it's all good. Then 32, 3, 4. Let me speed up the process. Then I have many blocks with 3D. Yeah, 3F. And then, first of all, I have a gap between 3F and 42. And second of all, I have just one block with a header 42, one block with header 43. And basically here I use the same statistical method. I try to select blocks. I try to select headers which most of data blocks have. We see that most of blocks have headers from 21 to 3F. And there is just one block with header 42, just one block with header 43, 3, and so on. And then empty blocks are going. So basically I know the range of headers now, and I can do that filtering by headers. To do this, I click to block filter. In here I select header, and now instead of set, I select range. So now I can set range of headers from 21 and to 3F, 21, 3F. Okay, and you see that it's all unchecked now. All those unnecessary blocks. Now I click to block sorter again. Okay. Let's go up. And it's much better. There is just one block with number 0, one block with number 1, 2, 3, and so on. So I've done now this filter by header thing. Now I need, we skip again banks. We'll discuss it in next case. Now I do this filter by LBN range thing. How will I do this? I just visually check until what number this LBN will grow. And we can see that it's growing. Yeah, and as usually, it's LBN range is located within the range of until 3FF. You see, the last one, it's 3C6, and this one is out of range. If I open it, yeah, I see just nothing. Well, the same nothing is here. It's tail of the logical image, so it's empty space. So I can manually uncheck this block now, or I can run block filter and set filtering like from 0 to 0.3FF. It will do the same things. So it will cut all that unnecessary blocks in the end. And once I did that filtering, now I can try to do what? I can try to check LBN chain. I should deal with duplicated blocks and missing blocks. Let's check if this case has it. Okay, I click to this button, check LBN chain. Yeah, and the very big, and there is a big gap between E0 and EF. So you see there are no any duplications, but there is a big gap between E0 and EF. So actually I can insert empty blocks between these two blocks, but it doesn't have much sense because you see it's empty space here. There is nothing on these blocks. These blocks have some garbage. Then there is empty space here. So basically, if I will insert that empty blocks, I will just do my logical image a little bit bigger. But there is no any data after this gap. And from file access point of view, it will not change anything. Actually, I can just, you see the chain is going good until DF, no, E0. Actually, I can just uncheck these 3 blocks because they're empty, and that's it. So this block will be the last block in logical image. And if I check the chain now, I see that no errors found. So everything is great now. I did cut that unnecessary end tail of logical block, that 3 blocks, and that's it. And now I can create logical image. Okay, logical image is done. I go to File System Viewer. And there we go. We have access to all the data. Some of data has red flags. That means that the header is corrupted. So it could be either because of some bit errors or some problems with reading, but mostly it's all right, it's all good. So that's SM controllers. Standard SM controller where you need to do standard steps for SM controllers. Is it all clear? Okay. Marbury is gonna be my indicator. If you say yes, then I proceed. All right, so let's see next case. Then the next case, I don't remember what's this. I did prepare. Let's see. No name. It's the bank thing, I guess. Yeah, so you see it's pretty old case. There is no inversion, there is no XORed transformation here. So yeah, it's pretty old case. And let's check its structure. The structure is very standard. We have 512 bytes for data, then 4 bytes for service area, and then 20 bytes for ECC. Okay, let's check service area. I scroll it to some data place, then go to service area. Yeah, and here service area looks like this. So it's what can we see here? There are 2 bytes. Let me zoom in. This and this byte, and they change value from time to time. So change value here, and then here, then here, and so on. So these 2 bytes, I guess they are LBN. And first byte, in most of cases, it's just FF. So it looks like the first byte would be header here, and then next 2 bytes would be LBN. Let's try to set it like this. Header is the first one, and then 2 bytes for LBN. Let's change color. It's bad one. Not much better, but yeah. So most probably that we have here a structure like this: 1 byte for the header, then 2 bytes for LBN, then 1 empty byte, and then 10 bytes for ECC, and then period repeats. Okay, so we selected header, LBN. Now let's go to markers table and check it. To do this, I set LBN position and parameters here. So I select LBN, then I set header and create table. Table is done. Now I go to markers table. I have something like this. And I start my normal usual routine. I click to block sorter. And I see the result. Sometimes this result may confuse somebody. Like your people see here F and they think, oh, that's big numbers, so probably inversion must be used. But in fact, no, because only first symbol is F. But then we have 3 zeros. And those zeros, it's a good one. I mean, it's the thing which I'm looking for here. And I can see that first I have two blocks with the zeros, then 1, 2, 3, 4, 5, and so on. So sequence is growing. Sequence is growing, and so we have here the case like here when first symbol of the first byte is not 0, is not 1, but F. It's okay, it could be. So I have growing sequence. And once I see growing chain, I try to make filter by header. If I will scroll the whole chain, I see that most of blocks have header FF. Well, to me, it looks like all of them have header FF. And just this one has header 00. So let me try to run this block filtering by header, set it FF. Okay. And then block sorter. By default, okay. So that 00 block disappeared, but now I have next case, next situation. I see that chain is growing, 0, 1, 2, 3, 4, 5, and so on. But you can pay attention, you can see that each LBN I have 2 times here. Like these ones, those ones, and so on. Basically, any LBN, here I have 2 times. And in this area, this column address, we see physical address of this block in the physical dump, and we can see that these 2 LBNs with the same LBN, with the same number, they are located on pretty different physical addresses, right? This one and this one, for example, this one and this one, oops. There is big difference. And this is how banks look like. That's the case where we have to deal with banks. And let me introduce these things to you. I think I'll need whiteboard for now. So sometimes, for example, this is flash chip, right? Memory chip. And the physical capacity of this memory chip, let's say 2048 blocks. So physically we have here 2048 blocks. But for some reason, controller can address or want to address only 1024 blocks. So 2 times less. And in this case, the controller will physically divide this area by 2. And this first half will be first bank, second half will be second bank. And first bank will have LBN 0000. Next bank will have LBN 0000, and so on for all of numbers for all of LBNs, we will see them 2 times. Sometimes physical chip may have, let's say, 4096 blocks, so 4000 of blocks. But controllers still want to address just 1000. So it will create 4 banks, and we will see repetitions 4 times each. Each LBN we will see 4 times. That means that we have 4 banks in this particular case. In our case, we see repetitions 2 times. And do you remember I paid you attention that physical address of each block of each LBN, it's quite different. Distance between them is quite big. That's because one LBN is located in first block, second LBN is located, sorry, in first bank, second LBN is from second bank. So that's the bank thing. In this example, we have, it seems that we have 2 banks. And if we go to this diagram, we see that we did filter by header. And right after this, we see that we have each LBN 2 times. That means that we have 2 banks. That means that we need to add those banks. And how do we do this? It's very easy. So once we found this situation, we should close the markers table. And here in parameters of markers table, there is option bank structure. So now it's empty because software doesn't know about any banks. And we can add that bank structure. So software will divide physical image by number of banks we will add, and will arrange blocks in according to that banks. So to add banks, I should click on this plus button like this, and here I can select number of banks. I saw repetitions 2 times, so I set 2 banks. Okay, so now I have bank structure here. After this, I need to create table 1 more time with that new thing with banks and repeat the steps. I click to block sorter. I see again the chain is growing. I need to make block filtering. Header, set, FF, click to block sorter again. And now it's good. Now I don't see repetitions 2 times because I have block number 0 in here, and second block number 0 I will find here. You see, after all the blocks which are located in first half of the physical dump. So I did add the banks. I made filtering by header. The next step would be check LBN chain. And here it's really important to set correct LBN chain, because as you saw, okay, let me show it again. Between these 2 banks, so we have blocks with data. Let me put it here. We have blocks with data. Chain is growing. And then after last LBN with number, we have many blocks, many FF blocks. And if we will keep these blocks in our physical image, so whole second bank will be shifted. And we will not get access to any data from the second bank. So we need to remove all these blocks very precisely. So let's see until what number we have the LBN chain. So it's 91, B, C, D, E, F, A0, 1, 2, 3, 7, A, B, C, D, A, E, A, F, B0, 1, 2, 3, 4, A, B, C, D, E, F. Yeah, so you see until F3BF, the chain is good. And I have data here. Then there is a big gap, F3, F8. And there is garbage here. So all those LBNs from here and until this block must be removed. To do this, I will go to block filtering, select LBN range. Just in case I can check last block from the last bank. So here I have 3BF, last block, and here the last block would be 3. So the value is much smaller. Here I have, I think it's some garbage. So the sequence is going from 0 and until 3BF. Yeah, here. That's the last block with data from the first bank. Okay, I go to block filtering and set F000, F000 and F3BF. Click OK, and you can see that all these blocks now unchecked. So they won't go to logical image and they won't shift second bank. All right, now I click to block sorter. Okay. And it should be good now. It should be okay. So now I proceed with this thing, check LBN chain. I want to remove duplication and insert missing blocks. Okay, let's do this. I click to this button, check LBN chain. And again, it's very good. The chain is very good until the end. So you see, it's very end of the chain. Until F142, it's good. Then I have 2 blocks with the same number, and then there is a huge gap, and all blocks starting from this point, they are empty. So actually I can uncheck these blocks, empty blocks. And I need to select, yeah, and that's the case where header doesn't help me to select the correct block with the same numbers. So you see that both blocks have number F142, this and this, and both of them have the same header, FF. So in this case, I should just have a look into the content of block, check the content, and I should check what I have before this block and after, and select the block which has, let's say, most similar content, like to neighborhood blocks. So I have here some noisy looking data, Then this block is almost empty and has something weird. And this block has again noisy data. So which one I will take in the logical image? Of course, this one. This one looks different from like average patterns which I had before. So I uncheck this, click to block sorter, and I believe that after this, the chain will be very good. This button. Why I don't have any response? Ah, yeah. So no errors found. So this means that the chain is good. All blocks go in ascending order. All unnecessary blocks unchecked. And now I can proceed with logical image creating. I click to create logical image. Okay. And there you go. There is good file system. Yeah, I did add 2 banks because each block was repeated 2 times. That means that the case has 2 banks. If we have 4 repetitions, then we add 4 banks. It could be 8 banks also. Yeah, number of banks may be different. Usually for modern controllers, we have just 1 bank. However, not always. Sometimes it could be more. Okay, so that's all for this case. That's everything I wanted to tell you. Now let's see the next one. The software just checks physical location of block. In here, you can see this address. You see physical address. So if software finds 2 blocks with the same number, and software knows about banks, it just puts LBN with a lower physical address to the first bank and with a higher physical address to the second bank. So just physical dividing of physical dump by 2, and all LBNs from the first half go to the first bank. All another also LBNs from second half go to second bank. Just analysis of physical location of the block. Okay, the next case, oh, this one is tricky. So that's also kind of old case. There is no XOR, there is no multiplane page allocation. But LBN here, it's pretty tricky. And many of you guys had problems with such LBN. So let's check it out. I go back again to the physical image, structure view. I have everything in structure but LBN and the header. The structure here, it's the next one. We have 4 data areas with the size 512 bytes. So 4 data areas go in a row. And then we have 4 service areas, each for one for each previous data areas. Okay, let's go into the first service area. And let's see. So in total, we have here 6 bytes. By the way, the last question in the chat, Andy, did you get the answer? I mean, did you understand it, what I said? Okay, silence means yes, then. Okay, then let's proceed. So 6 bytes. And we need to select 1 byte for LBN, 2 bytes for LBN, 1 byte for the header. In this case, it could be not that easy because, let's see, first byte is kind of stable, right? So we see that it's just FFs mostly. So it could be the header, right? Second byte has 2 lines. You see this? And it also looks like all blocks. You see, I will scroll it more slowly. That second byte value is also stable. Okay, there is no data here. So we have here just 2 lines. Let me zoom in. So now I'm talking about this byte, this one. Sometimes it changes value, but for 99% of blocks with data, it's just 2 lines. Okay. So I consider that header in this case could be this byte or this byte, right? And then I have 1, 2, 3 bytes which changes value all of them from time to time changes its value. For example, now I can see that this byte and this byte, the next one changes value, and this one is stable. But then, for example, in here, I can see that first byte, oh no, not here. Yeah, here, for example, first byte changes value too. So I can't see very clear which 2 bytes, which pair of bytes belong to the LBN in this case. I have, let's say, 3 candidates for the LBN here. And I don't know which pair will be exactly the LBN. So let me do just first guess, like first try. I will set the header as a header for the first byte. Second byte I will set as a test byte. And then I will take 2 bytes as an LBN. Like this. Okay. Now let's go to markers table, and I select here LBN, header position, and test position. And click to create table. open it and go to block sorter. Okay. And now I'm checking the chain. So it starts from 0. Then it has huge amount of blocks with number 1, 2, 3, 4. So it could be banks, right? Many banks. But I need to check whole chain. To make sure about this. And for example, here, I can see that I have the sequence until FF, but then there is huge gap, and it starts from 0, 4. And then from 0, 4, it's starting to grow a little bit. And then 0, 5. And you see, amount of repetitions is different now. I mean, I had a lot of same numbers until 4,000 something, like you see that many. But after this point, I have just like 1, 2, 3, 4, 1, 2, 3. So it's not the same number. And usually when we have banks, it's the number of repetitions is very stable. It's a 2, 4, could be 8, but you know, each block will be repeated 8 times, not like here. Some of blocks repeated huge amount of times, another block repeated 4 times, another block repeated 3 times, and there are big gaps. And these blocks, they have data, so it's not like some garbage in the end like we saw before. It's the data. And it ends like 0, 7, 1D. So overall, this sequence looks like it's growing, but it's not very good because there are different number of repetitions, there are big gaps, and it's not going continuously, sequentially. So probably I did mistake. Probably if I check this, I see ascending LBN chain, but it's not the chain like we saw before. It's not the chain that I want to see because of that gaps and repetitions. So the answer here is no. I don't see normal ascending LBN chain. And now I need to check, maybe LBN is inverted. But could it be inverted? Usually if LBN is inverted, we have a lot of FFs, something like this. I don't see it right now. Just in case, let's try to invert LBN and everything. But it won't be any better. It's even worse. So LBN is not inverted here. Probably there is Little-endian order. Probably there is a Little-endian order. So this byte, second byte should be first, and second byte should be, and first byte should be second. So how to change this order? How can I check if there is Little-endian here format? I can just manually switch bytes here in LBN position. So now I have 2050, 2051. I destroy the table, and I can set 2051, 2050 like this, and create table. and open the table. So I used the same bytes, but I changed order. And maybe with this order it will look better. I click the block sorter. And I have some 4, 5, 6, 7, 21, 100. So it's still not good. You see it's growing, but it doesn't grow continuously. There are big gaps. There are different number of repetitions. So it's not the chain which I want to see here. And if you remember, in here we couldn't say for sure that these 2 bytes are LBN. There is one more byte here from the right side, and that byte also changes value from time to time. And so what can I try? I tried these 2 bytes and it didn't work. So probably I should try another 2 bytes. What another 2 bytes I can try? I can try this and that, those 2. So basically, if I have 3 bytes to try, let me run whiteboard. If I have like 1, 2, 3 bytes, and I don't know which bytes exactly belong to LBN, I have 2 options to try. I can try this pair, or I can try this pair. It's not possible to have like this pair of 2 bytes. They must be together. They should stay together. So there are just 2 options, this one and these 2 and these 2. We tried the first pair. Okay, so now let's try second. I can remove this record and add LBN like this. So I skip this byte. I have 2 bytes for the header, probably some of those. And then 1 byte is skipped. And now I will work with these 2 bytes, okay? So I remove in a markers table previous LBN position and I select new LBN position. So it's 2051, 2052. Okay, let's create the table and open it. And go to block sorter, click to OK. It starts again from zeros. I skip it. And let's see what we have now. So group of 1s, 2, 3, and then 100, 100, 1, 2, 3, then 200, 200, 1, 2, 3, 300, 300, 1, 2, 3. So what can we notice now? First of all, if we will scroll, the chain will see that amount of repetitions is stable now. Each block we have 1, 2, 3, 4, 5, 6, 7, 8 times repeated. Like here, for example, 1, 2, 3, 4, 5, 6, 7, 8. So it's stable. And another thing, we can see that first byte now is continuously growing. I mean, value of the first byte. It's like, have a look. I have here 1, 2, 3, 4, 5, A, B, C, D, and so on. So it's growing. And second byte just repeats for values like 0, 1, 2, 3, 0, 1, 2, 3. So what is this? What should I think about now? Do you remember that LBN? Yeah, right. It's the Little-endian, not Indian, but Indian. Little-endian format. When the first byte is continuously growing, second byte just repeats the value. So let's try to change the order. I will just switch these 2 bytes here in LBN position. Remove it and type 2052, 2051 and create table. Then open table, block sorter. Again, zeros. And let's see now the second byte, that low priority byte, low order byte is growing like it should be. A, B, C, D, E, and so on. Then it's going until FF here, and then normally switch to 100. Then it's again going normally until 1FF here and switch to 200. So now I like it. Now it's much better. Now I have just a stable amount of repetitions and continuously growing sequence without gaps. I mean, just visually I can detect it. There could be some small gaps which I can't see visually. We will work out them later, sort out them later. But on this step, I just want to see visually good looking sequence. And now I have it. And once I have it, I switch to this square. I can proceed with a filter by header, banks, LBN range, and so on. So that's what we do when we don't see normal chain, normal sequence. We struggle a little bit with this checking and then switch to these ones. Okay. Now let's see the header. Do you remember we had 2 candidates for the header? This one and this one. So let's see. We have huge amount of blocks with LBN 0, and both bytes, I mean header and test bytes, they also have value 0. Then when we scroll it and start to see data blocks, normal data blocks, we can see that the header, I mean this byte which we assume being header, still 0, but the test byte, that second byte from service area, now it's 11. Right. So that means that our guess about the header was wrong. also. And the header here is not the first byte from service area, but the second byte. So we must use this second byte as the header. And we can see that most of blocks here have header 11. So 11 would be the header. Now how to sort these blocks? We basically can recreate markers table and set number of second byte from the service area for the header, but there is quicker way. We can just run block filtering and select here filter by test1. It's not obligatory to use the header. Name can be any. We can select any option here. So we just select test1, set, and 11. And OK. Now it's all unchecked. We click to block sorter. And it's even more better now. So it starts now from zeros, and they have 1, 2, 3, 4, 5, 6, 7, 8. Still 8 blocks with the number 0, then 1, 2, 3, and so on. And now I need to think about banks, right? Okay. Once I see 8 repetitions each time, I understand that I have a banks most probably here, right? So I need to add those banks, 8 banks, as you understand. So I go to parameters of markers table, click to bank structure plus, and set here 8 banks. So you see, this controller was really lazy and didn't want to address that number of blocks. It created 8 banks instead of that. And let me, well, and actually here I can set the header position as 2048, because now I know that 2048 is the header, and test position I can just remove. So create table, markers table, then regular clicks, block sorter, then block filter. Now already I use the header because I selected header, correct position for the header. And OK. So these empty blocks unchecked now. One more time, block sorter. I do this after each my transformation. And have a look. Finally, I have it look normally. 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. So now, if I will scroll it, at least visually, it's OK. It's going until 3C5. Then next bank starts, and so on. So visually, the chain is good now. And I will check it with the utility, with the software. So I click to LBN chain, check LBN chain. And let's see, I have here 2 blocks 97 with the number 97. Both of them have same header. So I need to select one, the one which looks better for me. And to select the one, I can just check data patterns before and after this block. Like, for example, this one, it's kind of similar. And select the one which looks more same to previous one and to next one, or the one which has more data, like in our example. Okay, let me highlight blocks. So you see this is block size now. It's like black color is one block, gray color is another block. And the first version has this data. Can you see this here? The first version has this data inside, and second version start is the same, but then it's empty. So it looks like this block has more data. So that's why I will select this one, just because it has more data. And I uncheck second one. Okay, let's check next. 2D5 blocks. And the same thing here. First one has data, you see at the very end of block here. And second one doesn't have data in here. So I uncheck it. And keep checking LBN chain. Yeah, by the way, this is the first case where we need to really work with LBN chain. You see, we have here duplications, and if we will not remove the duplications, we will have this problem. Okay, my screen is paused. Why? Here. Yeah. So if we will not remove the duplications, they will shift next data after the duplicated block, and the file system will be really corrupted. So we need to remove them. And this is what I'm doing now. So I remove this, then next one, 2 blocks with a 12C. And these two look, yeah, the first one has a little bit more data. You see this string. So I select that one. Next 2 blocks. You see there are 2 candidates and they're located near to each other. That's the first one and that's the second one. The first one has data here. This one doesn't have data. So I uncheck second one and keep selected the first one. And then C9. So that's the first block, content of the first block, and that's the second. End is kind of empty, and here I have data. So you see, in this particular case, many duplications have difference, and difference is that one block has more data, another block has smaller amount of data. If we create logical image and we see that part of many files are not correct, then we can try that option, which is not available now, but will be available in the next update. We can just check like integrity of file system, and it will check each file and will show from what file, from what block we have the duplication not removed, or we have that shift. Another thing that you may see now, some particular file corrupted, and if this file will be important for you, you may guess that probably, and you did that, blocks selection before, like I'm doing now. You may think that probably you selected wrong LBN, wrong block, and it's necessary to select another block. So it's possible to check what block this file is located on. You can check the number of block of that file, and then you can check if there are some another versions of that block. I'll show you when I will finish the checking of files of LBN chain. Okay, so it's good. Then 2 more blocks. Again, this one is empty, this one has data. And these blocks, they are just empty already. There is no data in these blocks, but let's remove the duplications anyway. Okay, so no errors found. I removed all duplications. And now if I check LBN chain, I don't see any errors, any mistakes. And by the way, let's see what I have between banks. 3C5. Yeah, so blocks are located. Can you share PDF file to start test or upload file over? So PDF file is shared already, and the video probably will be shared too. I will add PDF file again now. All right, so the chain looks good now. It has 8 banks, everything goes in sequence without any mistakes. And now I can try to create logical image. It's created. And let's go to File System Viewer. And there you go. Everything is good. I mean, at least flags are good. And now let's say that like this file is corrupted. It's for your question, Amarbir. And you do remember that you did that block selections. So you can make right click on this file and click through the option go to data start. So now you are in the place where that file starts. And then if you will go to navigator button here and use this option go to source, it will bring you to previous element. It's like when you click go to data, you were in logical image without service area and so on. And then when you clicked to go back, it jumped into the unite element on the same offset. And here you can check block number, because in logical image you don't have block number. Logical image doesn't have any service area. It's removed already. So that's why you go to unite, because unite still has a service area. It's here, and you can check the number of LBN here. You go to service area and you have LBN, and to check to see LBN and hex, you run hex structure view sync position. Yeah, it's here. So you see that it's highlighted now as a green color. So the block would be A00, A0. So now you know that the file is located on this block, and then you can go to markers table. Yeah, if the file is ultra important, you can analyze it. You go here, you find that block here, and check if there are some another versions of that block, and you can try to use that block, another versions of that block. The next case, I think it's case number 6. Yeah, we will finish case number 5 as the last one. Now it's case number 6. It's AU controller. AU controller, and let's see its service area. This case, it's pretty tricky because it has bed columns. So, I mean, before physical image looks like this. And if you will start structure analysis, you will not be able to find it because there are bed columns. And first of all, it's necessary to remove the bed columns. And yeah, this is the XORed key. And the thing is that bed columns here looks like a noise. It's, well, sometimes they're recognizable, but sometimes it's really hard to recognize. So it may take some time. It may take some time to remove the bed columns. For example, if you go to bed column removal here and edit, we can see that first plane of the case, of this case, is just empty. So controller didn't write data to this plane. And second plane has data here. It has data, but bed columns, well, now they are recognizable when I marked them. But for example, if we try to do this again, first plane still has no data, and second plane, for example, here, and now I start to scroll in order to search for bed columns. Aha. You know, these bed columns are recognizable because, yeah, I understand now. Because I did ECC correction, and after ECC correction, this dump was modified, and that bed columns now are recognizable. But before, those bed columns were not recognizable, and they looked just like the noise, just like this XOR data. And to remove those bed columns, it's convenient to use this way. So I can select XOR key. So data is XORed now. So I can select some XOR key which is more or less compatible to this controller. So I set this controller marking. Now I want to select XOR key which has the same page size, and this this device has 16 kilobyte page size. And service area is not XORed. So, for example, this key I can select and just page. And you can see that the manual XOR key extraction will not be discussed today, but maybe on some another webinar. And also there is a topic, there is an article on our website where you can find that information. As far as I remember, there is one. And now you can see that that bed columns, that XOR key works until first bed column, and then it's all shifted. So once I click here, I add this bed column, I can go next. Yeah, originally it looks like this, so just a noise. And next. So it's a very convenient topic also, bed columns removal on when they XORed with XOR key. Probably we will discuss it later. It could be another topic of the webinar. All right. So I did already the bed columns removal, and with this, if you remember, one plane doesn't have any data. So with this offset tool, I removed one plane, the first one. So I have just a second plane now and the data from second plane. So basically, this offset now is the source of data. And that's why I will search for LBN and so on this offset. Because before I was just, I did preparations for the physical image to make this possible, to make structure view. So this is how page structure looks like for this case. 1024 bytes for data area, and then 2 bytes for service area, then ECC, and then it repeats until the end, and the very end we have just some noise. Yeah, so here where data stops, and then we have just noise which looks like actually like a XOR key. So you may pay attention that the service area consists of 2 bytes only in this, for this controller, and those 2 bytes usually it's LBN for AU controllers. So here 1, 2, we don't have any choice, we don't need to select the good bytes, we just see that we have only 2 bytes for the LBN. Yes. There is some counter here. It looks like LPN logical page number, but very first page of each block has logical block number. So we don't pay attention on this LPN. We work with LBN. Sounds kind of confusing. Anyway, the thing is that we have 2 bytes in service area, and those 2 bytes for AU controller usually is LBN. Okay, so we just call them LBN, and that's it. Now there is no header, just 2 bytes, no header. That's the service area of AU controllers. Now we go to markers table, select that LBN and create table. Open the table and the same script. Block sorter, the first step, and now scroll the list. Okay, it's starting 1, 2, 4, 8. Then 100. So what do you see here? Let me scroll it slowly. Do you see that second byte, low order byte, is just repeated, like 80, 90, ABC, 80, 90, ABC, 80, 90, ABC. But first byte continuously growing, 17, 18, AB, AC, 26, and so on. And if I will scroll it, the picture will be the same. First byte is growing, second byte repeats same values, 80, 90, ABC, 80, 90, ABC. What is it saying to us? What is it saying to me? If first byte is growing, second byte is repeated. That means that I have here a little-endian order, right? Let's see. On our PDF file. Yeah, so the LBN may be recorded in little-endian order, and it looks like this. Higher order byte continuously grows. Low order byte repeats several values. So exactly like it's written in the manual, in this instruction. And what do I do in this case? I just switch order of the bytes in here in parameters. So I have 1024, 1025. I change it to 10. Destroy, yes. 1025, 1024, like this, and create table again. Open the table, block sorter, many zeros, then yeah, for this one there is no header. So many zeros, then 1, 2, 3, 4, 8, then 10. So you see it's kind of growing, but there are gaps. 10, 20, 40. Big gaps, so it doesn't look good. But now, have a look. From this point, from 8,000 thousandths, it's better. So it's like 8,000, 4, 5, 6, and so on. 74, AC. Then we have 9,000. So AU controllers have the first block starting from number 8,000. it starts from 8,000 and then goes until something. Let's see until what. A, B, C, C. So C 91, 2, 3. So this one seems to be the last in the chain. Let's check content of that blocks. Yeah, so you see that this one has zeros, zeros, zeros. It's all zeros here, so it's the end of logical image. And this one, there are a huge gap between those two blocks, and it has just some noise. So the last block would be C093, and the first block would be 80, because until 80, or sorry, 8,000, because until before 8,000, I have some blocks, but the sequence is not good. It's just not growing normally, like we saw before. So, and another thing which you may remember, that it's quite typical for this controller to start LBNs from 8,000s. So we go to block sorter and set LBN range 8,000, and it was C093, and OK. So all these things unchecked now, and I click to block sorter. And now I have many blocks with the same number, 8,000. But it's not banks, it's just repetitions of the same block. Because another blocks, as you can see, 8,001, 2, or not 2, or 3, 4, 5, 6, 7, and so on, we have just one copy, just one number. So since there is no header here, we can't uncheck, we can't remove by header those blocks, like outdated blocks or not used blocks or garbage blocks, but they still, so they stay in the chain and they have the numbers with the same like the block, which is good one. And in this case, we need just, again, visually check when header can help us, or when there is no header. We should visually check the content of this block and select the best one, the one which we suppose that the best one for this image has the best data, or correct data, let's say like this. So the first block, you see, it's there are some diagonal patterns which look more or less like a XOR or something like that. And so it's definitely not a block with a boot sector or MBR, because we expect to see here zeros, right? So we expect to see white color here, but it's just a noise. So we uncheck it. Next one is the same, and you see, this block looks much better than previous ones. Let's open hex, and we can see boot sector here. Boot sector, marker stable. So this block is good. And for now, we select this one. It's the best candidate for now. So this one is garbage, garbage, and so on. So you see, there were 1, 2, 3, 4, 5 blocks with the same number, but only one has good data. So that's the way how we select, how we choose which one to keep and which ones to uncheck by content inside. Then we have just one block with number 8001, two blocks with number 2. One has zeros, what is normal for the start of logical image. One has garbage. So we do remove that garbage, right? Because this garbage is not typical for start of logical image. And another thing that you can check content before and after those two blocks. Before we have zeros, after we have, well, data already. This method doesn't help, but it will help in another case later. Well, it may look like data, but actually data here, if you will analyze this case more precisely, you can see the data have here this pattern. You see, like, it's more randomized, more noisy looking pattern. And this one looks like diagonal things like a XOR or something. So just statistically, you can see that usually this pattern belongs to garbage blocks. Okay, so A, 3, 4, 5, and so on. Now let's check at least visual. Here we also have, so you see, like, block number E has this noise, F noise, then these diagonals, then again noise. So which one we will, and by the way, here we can use finally that method I told you several times before. We just compare content of candidates and with the neighborhood blocks, like before and after. Here we have noise, here we have noise, and in those two, one has same looking noise like those two, and this one has some pattern. So we uncheck it. Now let's use this option, check LBN chain, because visually it looks better. So let's check the chain with the tool. Okay, so two blocks with 80-20. One has diagonal patterns, one has noisy looking pattern. So we select the second one. One more. We have 3 even. So only one has noisy looking data, and those two have diagonals. 41. And check these diagonals. Yeah, and here is the specific thing about these AU controllers. The first specific thing that we saw here, it's that first LBN starts from 8,000. The next special thing for this controller is that LBNs go in sequence until 80 FF, and then there are some big gaps like 8581, 8780, and then it proceeds with the numbers 9000s, 9001, 9002, and so on. So sometimes like increment step of each byte may not be just one, like it was on all previous cases before. Like, for example, normally we would see here 80 FF, then 81 FF, 80, then 8100, 8101, and so on, then until 81 FF, then 82 FF, and so on. So it's not working like this here. It works like it goes until 80 FF, and then next block starts from 9000. So low order byte is incremented on 1 always. And high order byte, the first byte, is incremented by 10. So it was 80, then it's 90, then it will be A, B, C, and so on. Could this be that controller swapped the well, probably. Maybe like this. Maybe it's firmware of this controller was made to read it like this. We have what we have, and we see that numbers go like this. And why do I pay attention of you guys on this? Because you see here LBN step, and until now we didn't change this step. We always used like default values here, 1 1. But in fact we can change it, and the syntaxes of this step is here. So the first number stands for high order byte increment step, and the second number is for low order byte increment step. So if we had, for previous cases, we had this situation when we had 1 1 and it was growing like normally. After 0 0 FF we had 0 1 0 0 and so on. For AU controllers we have another case, another situation. We have 80, then 90, and so on. So to make this to adjust this LBN step for this case, it's necessary to set 10 instead of 1 for the first position. So now software knows that after 80 there shouldn't be 81, but there should be 90, and after 90 there shouldn't be 91, there should be A, and so on. And another thing, that between 90 and 80 usually there are several garbage blocks which we need to uncheck manually. In our case we have two of those blocks, 1 2. Okay, now if we, for example, if we leave this 1 1 and click on check, software will stop here because it can see the huge gap between 80 and 90. But if we put 10 here, software will understand that it's okay. After 80, there must be 90. And it was going good until 90 FF. Then we have 2 more garbage blocks between 90 and A. And again, it's going until B. I uncheck this one. Two more blocks between B and C. Okay, 2 blocks with the same number C000. One has zeros here, next zeros, previous zeros. So it looks like C0 must have zeros. So I uncheck the one with these diagonals. 2 blocks C8, one has zeros, zeros, and this one with the garbage I uncheck. 253, and the same case here, and no errors found. Well, actually, this question about MSB order is switched already here. So it's little-endian order here, and MSB it's the second byte, and LSB it's the first byte. And I think it will not do less manual work. It will not be correct. Okay, so finally we finished with this markers table. Now, last check. I switch on I click here, check LBN chain, and you see no errors found. So that's all good now. Now I go to create logical image, and there you go. File system is here. So what I wanted to show with this case for you guys, that sometimes step may be not standard like it was before 1-1, but it could be different. That high order byte may be increased by 10 or by 4, it depends on different cases. And sometimes you need to adjust that step. And yeah, all the pictures seems to be good. You don't see pictures. Okay, that's the thing about, that's the special thing about this case. And now the last one. The last case, it's the case number 5, this one. It's a SAM controller, quite old case. Let's see how it works. As usually, we go to structure view, and I want to find LBN and service, LBN and header. Structure here, it's quite simple. It's 512 bytes for data area, then 3 bytes for service area, ECC, and so on. So let's check this service area. And when we will analyze this service area, it also has some, let's say, peculiarities. We can see that first 2 bytes here, they look like LBN, right? From here to here we have one value, then next value, and so on. Third byte looks like LPN, logical page number. You see, it just changes same way for each block. So we have 2 bytes. For LBN, it's here. And this is LPN. And by the way, we have on our website an article where you can learn about all the structures, like how LBN looks like, how LPN looks like, and so on. So you can check it. Now let's just set these 2 bytes for LBN. Yeah, and we can see that this is LBN now and 1 byte for LPN. All right, so we got LBN and we don't see header for now, right? We will see it later. I will show you. So we have LBN. Now we go to markers table. We set LBN position, create table, open markers table, click to block sorter. And let's see what we have here. And it starts from 23BE. And then it's kind of growing. 23BE, 24689A. So yes, it's growing, and you see that it's each LBN is repeated 2 times. So most probably it has 2 banks, like these ones, these ones, these ones. Well, most of them. There are some exceptions, but usually we have them 2 times. But the thing is that it doesn't start from 0. Here you can see that it starts, yeah, there is no header, and it starts from 23BE. And that's weird. That's not what we want to see here. And this happens because of next thing. This happens because sometimes, especially the old SM controllers, they use 2 bytes for LBN and for header. So 2 bytes, it's 16 bits, and they use 10 bits of those 2 bytes for the LBN, and first 6 bits they use for the header. So before I said to you that LBN has 2 bytes usually, header has 1 byte. For these old devices, sometimes it's not true. Sometimes the structure might be like this. Header has 6 bits and LBN has 10 bits. And for those cases, it's necessary to apply special transformation mask. Mask used AND operation, and here you can see truth table for AND operation. And when we apply mask, it means that we apply some number, for example, this 3FF, with AND operation on each LBN. And what do we want to do when we apply this mask for the LBN? As we see that LBN has 6 bits, or sorry, 10 bits here, we just want to convert, to transform all these bits before, all these 6 bits, into zeros, because we don't want to make them influent on those part of LBN. If these bits will be zeros always, The chain will be much better. We will see that it's growing normally and that it starts from 0. Because, for example, normally the very first LBN, very first block, has LBN 2C00. It's typical for this controller. Very first LBN had this number. And you can see that LBN part is actually 0 here. And this header part has some data. So with the mask, we want to zero this header part and to not change the LBN part. And how can we do this? If we make AND operation, if we have like LBN and we apply AND operation using 1, these ones will not change original content, because have a look, for example, here in the truth table. If we had 0 and apply 1 and 1, it's still 0. If we have 1 and 1, it's still 1. So LBN is not changed if we apply ones in that mask. But if we apply 0, it will convert everything just to 0. So with the mask, we will make like untouchable LBN part of those 2 bytes, and the header will be converted into zeros. So we will remove these 6 bits from the LBN. They will be always 0, because 0 bit, let's say here, if we had 0 and apply 0, it's 0. If we had 1 and apply 0, it will be converted into 0. That could be a little bit complicated, but the good thing is that it's not very common, not very often happens. And once you understand this, it's not a big problem. You just know that there are 2 bytes, part of the byte belongs to the header. You want to remove it, you want to make it zeros. And 10 bits belong to LBN. You don't want to change it, so you set ones. For example, there could be another case when you have, like in theory, you have 12 bits for LBN. So for 12 bits for LBN, like this area is the header or nothing, and this area, this 12 bits belong to the LBN. So the mask in that case will be 0, 0, 0, 0 to remove this data, and these 16 bits would be just ones. So to understand what mask you should apply, you need, well, actually you should know that 2C it's kind of standard thing for this controller, and 3FF is standard mask. Another thing that you need to check what LBN very first block has. And very first block has usually a signature 55AA, right? So it's possible to search for 55AA blocks. For the blocks with that signature, you can do this like this. For example, here, test position. Offset of 55AA would be 510, 511, right? It's the bytes where 55AA signature is located. Then you click to create table, open the table. Yeah, and sort blocks by test. LBN, yeah, you said here test 1. So you see that's the block with 55AA. If I open it, yeah, that's the very first block. And it has actually the number 2800, LBN 28. If I run calculator, let me search for. Wait for a second. I'm trying to get calculator. Okay, so calculators here. And programmer. Here I will set 2800. And in the binary view, it's 00, 01, 0, 1, 0, and so on. So you can actually apply another mask, but I think that we have here 28 because of bit error. And normally we should see here 2C00. So 28, I think it's the bit error. A standard value would be 2C, like an I can here 2C. And we remove this part and we leave this part. So how do we do this? Once we understand that we have this case and we need to apply mask, we go to Visual Non-Tree Constructor, Share, and here in Markers Edit, we can run option LBN Apply Mask and set 3FF. And when we click it, you see that that's 28 was converted into 0000. Now we click to block sorter. Okay. I shouldn't see that many blocks here. Yeah, now it's looking better, and I can see that I have each LBN 2 times. So there must be two banks here, right? So let me add those banks. For now, it doesn't matter, this step. Yeah, but for this case, it's not okay. It should be, for now, I don't know actually, but it should be not okay for this case. Well, let me add the banks because I see each LBN 2 times. Each LBN 2 times, I will add banks, 2 banks, okay. Let me create table again. Open the table, block sorter. Do I still have that mask? Yes, I do. Yeah, and another thing that I forgot to set here that we actually, if you remember, I said that we probably don't have LBN, header. We didn't see it, but in fact there is a header. It's this six bits, right? So to use the header, I should set it like here. Visual non-reconstruct. Yeah, I still have it. So for the header, I set byte number 512 and create logical. And now block sorter. And yeah, finally I can do that analysis. I can see that the header now is changed, like for SM controllers. So it's 24, 28, and so on. And I need to find, so I have range of headers here. So I need to do the regular thing I did before for the second case. I go to block sorter and set it to sort by headers. I set header instead of LBN. And I can see that data blocks starts from header 24, 7, A, B, C, D, F, to F. Yeah, and then the next bank starts. So from 24 to F, then there is a big gap, and 44, 48. So it's not the good header. Well, we can do this, but it doesn't matter because it won't change many things. It will bring us the same result. So we just don't change it because we can use it without that mask. It is still, let's say, enforceable for us, and it's okay. However, yeah, we can use this mask for the header too, but it will not make big difference. So 24 to F, block filter, I set header, range 24 to F, okay. And block sorter again. Block sorter again. And finally, we have normal sequence. 0, 1, 2, 3, 4, 5, blah, blah, blah. So the hardest part here is to understand that 2 bytes have header and LBN inside together. And with the mask, we zero out first 6 bytes, and then we make rest another bytes unchanged with ones. Standard mask, standard case is when we have 2C, 0, 0 for the first block. So normally we apply 0.3FF. However, there could be another cases for more modern controllers, and you can how to understand what mask you should apply. You should check what the first block has, what LBN first block has, and then you will see what bits must be turned into 0 in order to make LBN looks like 0, 0, 0, 0. That's what we do with the mask. We just make it look like just zeros. Okay. And now let's check the LBN chain. Okay, two duplicates here, but it's all empty, so it doesn't matter which one I will select. To CD. Well, and here I have some data and no data, no. So anyway, it's empty space. Both of these blocks doesn't look good, but since it's empty space here, I think it won't make any big difference if I keep, for example, this one. Okay, next. Again, and again, those blocks in empty area, so it doesn't matter which one I select. And no errors found. So block sorter. No errors found, and that's it. Okay. Now let's click to create logical image, and that's it, I hope. Yeah, right. Yeah, mask part was kind of confusing, but I think that later when you will see the video, you will get it better. And I think that this slide explains a lot. LBN part, header part, and yeah. All we do with the mask, we should convert, like in this case, 2C into 00. So we had 2C on the block number, on the very first block. If we apply mask 3F, we will make it look like 0000, and that's what we want. Mask is applied when not all bits from 2 bytes belong to LBN.